Good afternoon on Monday, April 28th. We need to get caught up on a couple of things here, so we're going to study quarks. Quarks, besides being a word that's fun to say, are kind of interesting because they are so small that we have no technology that we can see them with. But we theorize them, and our theories make sense. We can get some evidence of the particles by using things like the Large Hadron Collider, the LHC, the device that can accelerate small particles to nearly the speed of light and crash them into other small particles, particle accelerators. And so it's kind of cool. There we go. This was designed to kind of condense what we need to learn about these things for a Regents test. We don't have a Regents test this year now, but I still want to make sure we know what these words mean. Okay, one thing you'll see throughout this publication or this PowerPoint, including in the little footnote on the bottom, is the term CERN, C-E-R-N. And there it is on the top. I won't burden you with my French pronunciations, but basically it's the European French Council for Nuclear Research. So CERN comes out of that, and if you speak French, then you can practice it. It's a intergovernmental, several governments work on it, and they work carefully with the Large Hadron Collider people. So it's a bunch of smart people, and things that people have known for a while. We mean you and me and our world and my dog and Tyburn Academy and New York State and everything made of particles. And everything in the universe seems to be made of these particles. We can sort of make the assumption that what we see and learn here about particles probably applies universally, although there may be some weird little things we don't know about. So we know now about 4 kinds of matter, ordinary matter, and those particles are called, well, we don't know about this yet. Particles are called up quarks and down quarks. They have funny names. Electrons, you know what electrons is from earlier courses. Electron neutrinos are a weird little electron-like particle, but it doesn't have an electrical charge. That's where the word neutrino or neutral comes from. And well, basically that's just a picture of a astronomical picture of a star with having had some kind of explosions, and those are these shock waves coming out of the star, and maybe it was a black hole predecessor. We don't know. Just kind of a cool picture. Okay, smallest particles. If you take 1,000,000 atoms, 1,000,000 is a pretty big number, that would fit across the width of one of your hairs. But they're actually pretty big compared to things that CERN accelerates and studies. Now, 99.9% of an atom is empty space, which is really kind of an interesting thought. If you walk into a brick wall and hurt yourself, 99.99% of what you walked into is empty space. Well, try to explain that to your head that banged into the wall. So it's empty space, but it's held, things within that space are held together really strongly by strong and weak nuclear forces. So anyway, CERN is interested in figuring out what's the 0.01% that's not empty. And the only way to really see things like that, can't see them with a regular microscope, optical microscope, can't see them with a electron microscope, which uses a beam of electrons to look at things. So it could look at something approximating the size of an electron, but that's huge compared to the particles that CERN wants to look at. So they put the word microscopes in parentheses there because they are using an accelerator and detector to act like a microscope. They're giving us kind of a crude picture of an electron and a proton. That would be a simple hydrogen atom, the simplest element. But, let's see, by accelerating particles with these strong magnetic and electric forces, we can get them to go into very high energies, approaching the speed of light, and then we smash them into a target, which could be some material, or to each other. And in doing so, we produce sometimes new particles. there were a lot of concerns that when the Large Hadron Colliders started up, they were going to produce little baby black holes that were going to float out of the place and start sucking up the world. And scientists knew that was not going to happen, but we all know from the internet age that a rumor or a conspiracy theory can get going. So we thought the government was producing baby black holes. So far, nobody's been eaten by one, so I guess it's falling back. And when we shoot these particles, we can get conversion of mass into energy, and Einstein's equation equals mc squared, but only certain masses are found. So they're showing you a crude picture here of an accelerator. I don't know why the graphics on this are not very good. And we can use magnetic fields and electric fields, and we have a big circular thing. I think this is 26 miles around. That's not a lab in a room somewhere. And then we accelerate with 1,000,000 volts here, and then we can study them. And they're shooting this electron around. So there's Einstein's equation, but you're actually going to have to use that for homework coming up. E is energy in joules, m is mass in kilograms, and c is the speed of light, 3.0 times 10 to the 8th meters per second. And it's called that, as you may remember, because it comes from the Latin word celeritas, which means swiftness. And if anything is swift, light is. Okay, so quarks beginning. Well, the particle collisions are organized into the middle of huge detectors. Such great concentration of energy produces new particles, and they're studying these particles as they fly away from the collision point. And as a kind of a picture, an electron and a positron. A positron is a chunk of antimatter. It's the equivalent in mass to an electron, but it has a positive charge. Electrons have negative charges. And so antimatter exists, and it's when you combine matter and antimatter, you get a fairly decent explosion, not like dynamite, but you release a lot of energy. And there's also other forms of antimatter. It would be an interesting fuel if we could figure out how to produce it and store it. And so we have then quarks, which make up these primary particles. Up quarks and down quarks are embedded deep inside protons and neutrons. Only those two things, protons and neutrons, are all that we find in the nucleus, no electrons. And inside those things, we have quarks. Now, quarks, the next question is, well, are quarks made of something if we can keep going down? And that's a hard question to answer. Some scientists have proposed a particle called a preon, P-R-E-O-N, as the constituents of quarks, and that may or may not be true. It's kind of a hypothetical theory. There's another particle called a prion, P-R-I-O-N, which is a biological particle, a type of protein that's actually associated with the changes in the brains of animals or people when they get mad cow disease, which also affects cows, obviously, and even some things as Alzheimer's. So anyway, prion and preon are different terms, and preon is the one that might make up quarks. We're not going to go down that far. We're going to stay at the quark level. And these things are held so tightly into each other in the nucleus that we really can't pull an individual one out, the strong nuclear forces. So here's a picture of a neutron, and it's made up of a down quark, and an up quark, and those things have electrical charges, but in a neutron we know that they need to cancel out. So we can define electrical charges in terms of parts of the charge of an electron that these guys have, and we'll do that in a minute. Here's a proton. Proton is an up quark, and down quark. A neutron is a down quark, and up quark. Sounds kind of funny when you talk about these things. The strong interaction of these guys is what holds them together, so that's what keeps a proton together. It's not like springs, that's just a visualization of it. Nature uses 4 different glues to make particles stick together. We've talked about these in our physics class before. Gravity is the force that acts over the longest distance, depends on masses. And then we have electromagnetic forces, charges like plus and minus electrical charges. That's why you can attract something to another particle. If I rub a balloon on a wool sweater, it'll stick to the wall, or if I put two of them on a string, they'll push apart. That's electromagnetic forces. Gravity is only a one-way force, as you know. Electromagnetic forces can work two ways. And then we have the strong and weak nuclear forces. So we're going to talk about those briefly. Strong interaction carried by this term called gluons. The people have fun making up these names. Gluons basically is like glue. Sticks the quarks firmly together in protons and neutrons inside the nucleus. So we've got quarks and gluons. It's a vocabulary list that's weirder than anyone you've ever seen before. Okay, strong interaction has the curious property that if quarks get farther apart, the interactions between them become stronger. And if you remember the interaction for gravity and electromagnetic forces, on the bottom term is distance squared between the particles. And if you make the particles get further apart, the strength of the force, whether electrical or gravitational, falls off exponentially. Well, here it's weird because as they get further apart, the forces become stronger. This means that they are free to roam inside their nuclear cages, sort of like the nucleus, but they can't escape, sort of like the animals in a zoo. It's kind of a weird analogy, but it's not bad. The particles are not tightly held. As they get closer to each other, they actually have more freedom of movement. And we're talking really tiny distances here. But as they get further apart, the forces holding them all together gets stronger. So I'm not sure what that little picture is. That's a proton with an up-up-down quark in a hydrogen atom. And those little guys are, I guess, quarks. Okay, kinds of quarks. Fundamental building blocks of matter. They build neutrons and protons and many other particles called hadrons. There are 6 different types of quark. Each different quark type is called a flavor. Physics people are just weird. And now the pictures were not produced by the physics people. Somebody had fun with these. Up quark and down quark. Charm quark and strange quark. And top quark and beauty quark. Well, there's strange. And there's some people actually have different interpretations of these. Point is, there's different types of quarks, and we can identify them by their characteristics. Okay, this is the more typical up, down, charm, strange, and top and bottom. I don't think beauty is really one of them. And we have a tiny little mass that can be expressed in gigavolts divided by light squared. That's a very weird unit, but basically you can compare these numbers. So the largest quark is the top quark, 175 of these units, and the smallest quark is the down quark with 0.008 units. And more importantly, the electric charge in terms of the charge of an electron. Up quark is 2/3 the charge of an electron. Down quark is -1/3. Charm quark is +2/3, same as this guy, -1/3. So there's similarities between these, but not in their masses. And over here, so we can add these numbers together. We can add these guys together to get a plus charge. If we take, well, how would we get a +1 charge? +2/3 and +1. Let's see, if we take 2/3 and -1/3, we'd get a +3/3 or +1. So you can build a plus charge and a minus charge by using these fractions, but you got to be careful and add them together right. We don't need the quarks make up neutrons and protons. They don't need to make up electrons because we're measuring their charges in terms of electrons. Okay, so how do we know they're real? Well, research. The answer is simple. We found hundreds of different particles. When they crash things together, the particles had only certain distinct masses, so not all different masses are found in nature. This was an important clue that something special is going on. If you assume that smaller building blocks of which all of these particles are built of, then the picture is complete. Anyway, they're using logic and the fact that they find certain particle masses and certain electrical charges. So, and it's a theory. We've never seen these guys, but we, for hundreds of years, talked about atoms. We had never seen them. How can we detect these particles? Well, the detectors record the traces of particles that are too small to be seen, but we can see traces of them. And here's our electric signals, and we crash these things together, and we're getting signals then from these interactions. That's not a very good diagram. You can actually get, if you type in diagram for quarks, you'll see some pictures of actual traces of things. Here's the size of this accelerator. That's one little cross section through it. Looks like some kind of a spaceship thing. Here's people down here on the bottom. Pretty big. Imagine making a 26-mile tube of those in a circle. A lot of work. It has to be underground, not overly deep, but it has to be underground to shield it from some of the particles that are floating around in the atmosphere, cosmic radiation. So the only type of particles that they can find in large quantity underground are called neutrinos, because with their neutral charge they can travel through the Earth pretty well. Okay, how do particle detectors work? Particle passes through the detector, collides with atoms, and kicks out electrons. Electrons are attracted to a positive wire hanging nearby in the detector. It's not really a wire, it's a coil. And electron pulse on the wire is amplified and sent to a computer. From the position of the wire and the arrival time of the signal, the computer reconstructs the path of the particles coming off of the collision point. And I don't know who thought of that picture, but I guess they're trying to show that CERN is the big dog, and we're looking at two little particles that are being produced. It's almost like my Akita. Okay, that's basic. It's they're fascinating. The degree that they're tested in Regents test is not very great. We would probably spend another day or two on them, but it is fascinating, that sort of stuff. So you have an assignment to do. It's 4 problems, and I gave you some help to do those. And if you look at the weekly schedule, there's something perhaps more fun on Friday of this week. Take care and be safe.